I'm going to present our work titled Automated Severity-Driven Patch Management. This is joint work between our industrial partner Siemens and UFRJ. We have many co-authors here because this is a work that has been evolving over the past few years. The work is motivated by the prevalence of vulnerabilities. So we have more than 250,000 vulnerabilities at the National Vulnerability Database maintained by NIST. And this impressive database has a lot of information about each vulnerability, including its severity, but severity depends on time. And this is because over time we have the release of public information about vulnerabilities. We have new proofs of concept, new functional and fully functional exploits. And the question here is how to track the evolution of severity given the publication of this artifact. So our work is clearly related to the vulnerability life cycle, which involves the discovery of vulnerabilities, patching, weaponization, and exploitation of these vulnerabilities in the wild. Our key focus of this work is on the time to weaponization and how weaponization impacts severity of vulnerabilities, which is critical. For instance, for patch management, we need to rank vulnerabilities based on their severity so that we decide which vulnerabilities are more relevant than others. So there is a classical severity scoring system, which is CVSS, and it stands for Common Vulnerability Scoring System, and it's divided into subscores, which are in two classes, the class of exploitability and the class of impact. The class of exploitability involves access vector, access complexity, and authentication, which relate to how easy it is to exploit a given vulnerability, and the class of impact involves confidentiality, integrity, and availability, which relate to what's the impact of a given vulnerability in case it can be exploited. So CVSS is great if we want to understand what occurred in the past, if we want to understand properties of vulnerabilities that have been analyzed, let's say, in a lab. But how to track the evolution of the severity? So CVSS does have an extension which accounts for CVSS temporal metrics, but still this extension can only be used if we have historical data about this particular vulnerability. It does not encompass the relation between vulnerabilities, or it does not encompass how can we learn properties of a given vulnerability if we know properties of other vulnerabilities in the same class. And actually that's exactly one of our goals with this work, to fill this gap. So the temporal analysis is key when measuring severity. We want to know how long has severity been kept high, or how will severity evolve in the coming days. So to answer these questions, we need a model that not only explains how CVSS might have evolved in the past, but can also be used to predict how CVSS will evolve over the future. And weaponization information is key to track severity. So to collect data about weaponization, we use this framework here. So we collect data from multiple sources, including ExploitDB, NVD, and then we do a matching to relate to which vulnerabilities a certain set of exploits apply to. And then after doing this matching, we classify the vulnerabilities into groups, and then we extract the CDF of weaponization time for each group, and then given a new vulnerability, we try to detect which group does it pertain to, and then having the CDF of time to weaponization for that group, we combine this information with information from CVSS to then infer how will severity evolve for this new vulnerability. To be more concrete, here we show a snapshot of NVD and a snapshot of ExploitDB. So from NVD, we collect data such as the vulnerability identifier, textual description, and so on. And from ExploitDB, we capture information about the exploit publication date and possibly even exploit maturity. And from this data, we build plots such as this one, which shows the CDF of time to weaponization, which is the CDF of the time in which that weapon was released minus the day in which the vulnerability was reserved. So the vulnerability was set at NVD. So we see that for some vendors like HP, we have a significant fraction of vulnerabilities for which the weaponization, the first weaponization occurred before the vulnerability was disclosed. So this means that we were able to find weapons for which the weapon disclosure date was smaller than the vulnerability disclosure date. But for Adobe, for instance, we see this is much rarer. So for Adobe, the vast majority of vulnerabilities have a weaponization date which occurs after the CVE reservation date. So this sort of pattern can then be combined with CVSS to produce a metric of how severity evolves over time. So this is our key insight here, our key solution. The simplest solution that we could think of is to use the CDF of time to weaponization to scale the CVSS values. So we simply multiply, in the simplest case, we simply multiply the CVSS value by the CDF, and then we obtain a new curve which shows how severity evolves over time for a given vulnerability. So here's the general workflow. Given a new vulnerability, we try to identify whether we have enough information about its vendor, about its product. If we don't have enough data points, we use machine learning to predict a broader class of vulnerabilities. And then once we have the set of vulnerabilities in that class, we can compute CDF, such as those that we have shown in the previous plot, and finally produce curves of how risk evolves over time. We did this, for instance, to Heartbleed and to WannaCry, and we obtain curves such as those that we will show in the upcoming slides. But here we just summarize the key idea, which is to combine two models: a model of time to weaponization for a class of vulnerabilities, and a model for severity, which is CVSS, and the combined model shows how severity evolves over time. So again, the plot that we showed in the previous slide, CVSS, for instance, for WannaCry, which is well known, and then in the X axis here we have days in CVA disclosure. In the y-axis we now have CVSS. So we relate the plot in the left, which had numbers varying between 0 and 1 in the y-axis, to the plot in the right, where we now have values varying between 0 and 10, which correspond to CVSS values. And the way to relate one to the other in the simplest case is to simply multiply the CDF curve by CVSS base score to then obtain a curve showing how CVSS will evolve over time. And we can do this based on vendor, based on the machine learning model, which we call here predictor-based model, or we can do this simply looking at the exploit history-based approach. We can do this in multiple ways, but the basic idea is that each of these ways will provide a different perspective towards how severity evolves over time. We don't want to use simply vendor product information. If you want to use something more let's say abstract, related to features and hidden patterns, we then use standard classifiers such as naive Bayes, SVMs, or neural networks to classify the vulnerabilities into groups based on the time to weaponization. And then we see that even with simple methods, we are able to already get classification accuracies around 60% for the class in which the vulnerability which is found. In this simplest case, you consider 4 classes. One class in which the vulnerability had its time to weaponization much before CVE disclosure, slightly before CVE disclosure, after CVE disclosure, much after CVE disclosure. So given these classes, we then compute for each class the corresponding CDF of time to weaponization. So to conclude, we have lots of unstructured data available about time to weaponization. So we propose a framework to collect and combine this data with CVSS base scores. Our outcome are curves showing how severity evolves over time for a given vulnerability or a class of vulnerabilities. And future work involves including more sources of data about exploits, refine the notion of accuracy, and consider new ideas about how to group or relate vulnerabilities. Thank you so much for your attention, and we are happy to receive questions, comments, and suggestions.